Bom dias. In the last lecture, I explained what sparkling saddle connections are. I will recall that now, and they give rise to what will be the subject of the lecture today, numeric invariance of generic families. I do not write down what families are considered, and I will say this in words. These are families of vector fields, smooth families of vector fields in the two-sphere, or in the plane, if you wish, with an absorbing disk, for instance. So, first of all, I will recall you what are sparkling saddle connections. And this long title will be replaced by this abbreviation. We have a hyperbolic saddle with a saddle inside whose separatrix winds. The hyperbolic saddle is with a saddle loop. Two separatrices do coincide. And there is another saddle whose separatrix winds from the loop. And then there occur sparkling saddle connections. And for those who hardly took the picture that I plotted here, and I will repeat a little bit later, I want to show another picture of sparkling saddle connections. Consider a non-hyperbolic limit cycle. That is, the orbits from outside do wind to the cycle, and from inside do wind from the cycle. When the parameter changes, the cycle may vanish. And the blue orbits can enter to the region where the yellow ones were. So it is an easily understood picture. Is it okay? Is it okay? When we change the parameter, the limit cycle, multiple limit cycle vanishes, and the regions outside and inside become connected. Okay? But it may happen that outside there was a saddle, and inside there was a saddle. And for some particular parameter values, these two separatrices would coincide, and we will get a saddle connection. The smaller positive epsilon is, the more winds the blue separatrix makes before it meets the yellow separatrix that although made a lot of a lot of wines. And on the parameter axis, epsilon, you get a sequence of parameter values that correspond to the sparkling saddle connections. The smaller is this particular value, the more wines, the longer the separatrix connection is. So the picture here will be like this. And once again, I will not repeat this picture for the parameter value. There will be a sequence of parameter values that tends to 0 and corresponds to sparkling saddle connections. So this is what I wanted to say about sparkling saddle connections. Suppose that the characteristic number of the saddle is the saddle O. It corresponds, as before, to two eigenvalues of the linearization, one negative, another positive. Their ratio, better to say the magnitude of their ratio, with the negative eigenvalue in the numerator is called the characteristic number. When you know lambda, you can characterize the asymptotics of this epsilon n. Let us consider, I will yet repeat this picture. Epsilon n. A natural question is, what is the asymptotics of these epsilons? It appears that for a non-hyperbolic cycle and for a saddle loop, the asymptotics are quite different, and I will need this letter asymptotics. So asymptotics of sparkling saddle connections for the saddle loop. It is the following. It occurs that the sequence of parameter values for which the sparkling saddle connection occurs decreases fantastically fast. It decreases not exponentially, not like a geometric progression, but rather double exponentially. And it makes sense to take the double logarithm of the values epsilon n. So the value of epsilon n is small, its logarithm is negative, so the next logarithm may be taken of the magnitude or of the inverse logarithm of epsilon n. I recall you that lambda, the characteristic number, is smaller than 1, and the knowledge of this lambda only allows you to write the following formula. Log lambda, as it is smaller than 1, is negative. This value is positive. And this is O large of 1. It is an old result of Dumortier and Roussary, and a new result of two my collaborators and myself is more detailed. The same thing equals to the same thing plus some beta plus some theta times this very lambda to the n plus O large. As lambda is smaller than 1, these are the decreasing geometric progressions. It is due to Ivan Shilin, Stas Minkov, and myself. I will not use this formula, though it describes extra numeric invariants of the specific families. But I want today to give you the major fact existence of at least one numeric invariant. But I want to write this in the simplified form, an arithmetic progression plus something tending to 0. And let me stop here for a while. And discuss the question about equivalence of the nearby families. I do not give for a while a formal definition of the equivalence. My arguments now will motivate this formal definition, and I will give it in a few minutes. But let us consider two families, a saddle with sparkling saddle connections, and imagine that you have the second family like this. So the pictures are similar, and the parameter is, say, delta, and there are delta n, or delta m, another index. So you have two families with the separatrix loop and with sparkling saddle connections. And you want to say that they are, in a sense, similar, equivalent. And for that, you will make the following construction. For any vector field of the first family, you will find a vector field of the second family with the homeomorphic phase portrait. But the question arises what vector fields to choose. They do depend on the parameter. So you should first make a homeomorphism of the parameter spaces, in this case of the one-dimensional line. And certainly, if we want that the vector fields corresponding to, say, epsilon 0 and h of epsilon 0 would be orbitally topologically equivalent, have the homeomorphic phase portraits, then you should map the points corresponding to saddle connections to the points corresponding to saddle connections, and vice versa, non-corresponding to non-corresponding. So the homeomorphism H, first of all, brings these two sequences to each other. And then you have a phase portrait corresponding to this value of the parameter, and you want that the phase portrait corresponding to this value of the parameter should be topologically equivalent. So intuitively, for the two similar, to the two nearby families of this origin, such an equivalence relation does exist. And this motivates the following formal definition. Equivalence and structural stability of families of vector fields. Now, the number of the parameters may be arbitrary, and these are glocal families. This is abbreviation for vector fields. Glocal families are families of vector fields on the sphere. From here comes global character of the family with the parameter ranging in an arbitrary small neighborhood of of 0 in the k-dimensional parameter space. This is the local part of the family, so the family is global in the phase variable and local in the parameter space, and this is a glocal family. So by definition, two glocal families V, which is a set of V epsilon, and W, which is the set of W delta, with the bases, this is called base of the family, with the bases of the same dimension, are equivalent I abbreviate equivalent, provided that exists a map H which brings epsilon x. Epsilon is in the parameter base, x is in the, I did not write the vector fields where. First of all, on a closed manifold M. Second, M will be always the two-dimensional sphere, but it makes no sense to give the definition only for the sphere. It is a general definition. So these two vector fields are equivalent, provided that epsilon is in the base, x is in the phase space M, and the parameter value of the image depends only on the value of the parameter here. And here is h epsilon of x h is a homeomorphism of the basis of the families. This is a different neighborhood of 0 in Rk. And h epsilon is an epsilon-depending homeomorphism of M to M that provides the orbital topological equivalence of the vector fields V epsilon and WH of epsilon. That brings the phase portrait that is the set of all the orbits of V epsilon to that of WH of epsilon. So I take the vector field corresponding to this epsilon in the first family and the vector field corresponding to this parameter value in the second family.
In the parameter space, it's also homeomorphism, continuous.
On the parameter space, it is, on the parameter space, I did not write, and I always write this, H is a homeo for sure. Thank you. I just missed to put this word here. So, definition of equivalence of the families is, in a sense, tricky. In some old texts, it was required that the homeomorphism H epsilon would depend continuously on epsilon. And this seems to be a very natural requirement. But based on a wonderful theorem by Newhouse, Pallas, and Takens, Roussari discovered that some very similar families should be non-equivalent if we want that H will be continuous in epsilon. So no assumption on dependence of H epsilon on epsilon is required. And this is called weak equivalence, and we will restrict by that. This is weak equivalence. So, I want to find some obstacle to equivalence of families of vector fields in the sphere. Before giving you an explicit example, I will just give you some heuristic ideas of why the equivalence may not take place. When we have a family with sparkling saddle connections, then a homeomorphism of the parameter spaces should bring a sequence, one sequence of sparkling saddle connections to another. In case of the saddle loop, these two sequences in the double logarithmic scale are slightly perturbed arithmetic projections. And it is very easy to make a homeomorphism of a line that brings one arithmetic progression to another. It might be only even affine. You take an arbitrary arithmetic progression with the positive coefficient alpha, and you can make an affine coordinate change on the line that will bring this arithmetic progression simply to natural numbers. So you have two arithmetic progressions, you bring them to natural numbers, then you make an identity map that brings natural numbers to natural numbers. But suppose that for some reason you will have not one arithmetic progression on the line, but two arithmetic progressions. Topology of the pair of arithmetic progressions. So let us forget for a while about bifurcations, and let us think about one-dimensional topology. Consider two arithmetic progressions. All the coefficients will be positive. I will not write that. So all the arithmetic progressions will tend to plus infinity. This is one couple of arithmetic progressions. And this is another couple, the same with tilde. The question is, what is the obstacle to the existence I will even require the homeomorphism not of the whole positive ray, but of some positive ray going to infinity. When there exists a homeomorphism that brings one pair to another, not literally the whole pair, because it is defined in some neighborhood of infinity, so it ignores the first terms. But in any case, a homeomorphism that will bring the tail of the first progression to the tail of the first progression in the second couple, and the same for the second progression. First of all, we can simplify the problem as I have said. We can make two affine maps on the line, one adjusted to the first couple, another adjusted to the second couple, and transform this couple. This arithmetic progression will come to natural numbers. So we will have an plus b m. This is one couple, and another a tilde n plus b tilde m. And we have natural numbers here, natural numbers here, and we are looking for a homeomorphism that brings this sequence to this sequence. I did not yet plot the second sequence. Say it acts like this. The only thing to change that remains is a homeomorphism of this segment to this segment. But we already know that the natural numbers are mapped like this. So probably some of you will guess a necessary condition, or the condition like this. If A and A tilde are bad, then the homeomorphism does not exist. Can somebody guess what does it mean bad? Let us take another arithmetic progression. So for one progression, A will be smaller than 1. For another, it will be greater than 1. Does a homeomorphism that brings natural numbers to natural numbers and yellow points to yellow points, does such a homeomorphism exist? What do you think? No, because it brings this segment to this segment. Here the yellow points exist, and here they do not. So can you now guess a necessary condition for the existence of such a homeomorphism?
That there are like the same amount of yellow points between the sequence. If you take like the intervals and the number of yellow points here, and take that sequence must be the same as in the other progression.
So for what relation between A and A tilde this will be definitely violated?
If the A's are different?
Yes, exactly. If A and A tilde are different, then the homeomorphism does not definitely exist. So the answer yes implies that A equals to A tilde. And this is a topological invariant of a couple of arithmetic progressions. And I should say that this is an elementary problem if you will have say, quiet quarter an hour, you would prove this rigorously. And this is the main goal of what I wanted to say in this subsection, that two arithmetic progressions on a real line is a topologically tricky object, and if the two pairs are equivalent, topologically equivalent, then the coefficients are equal. This subject may be strongly developed, and these are not the only topological invariants of the couple of arithmetic progressions. But I will not discuss other invariants. I will rather say that if you have slightly perturbed arithmetic progressions, everywhere you put plus O small of 1. And the two couples are topologically equivalent, then this O small of 1 changes nothing. And topological equivalence implies the existence of this numeric invariant. So now let us look for the miracle. Let us look for a family of vector fields for which there is a one-parameter subfamily with two sequences of sparkling saddle connections. And I will draw you such a vector field. We call the face portrait of this vector field tears of heart. And it is a codimension 3 vector field with the following face portrait. There are two hyperbolic saddles, L and M, and 3 saddle connections, one like this, another like this, and the third like this. So this couple of connections resembles what? The heart, yes. And this, if you turn it vertically, is like a drop, like a tear. So this picture is tears of heart. And suppose that inside the tear you have a saddle whose separatrix winds from the tear. And outside you have a separatrix, a saddle whose separatrix winds towards the polycycle. Probably I forgot to say something in the previous subsection. If we want to turn back to this couple of arithmetic progressions, you easily note that A equals to the ratio alpha to A large, and A tilde is alpha tilde to A tilde. So we have in the previous version, we have this equality, and we will use it analyzing this picture. So, in fact, this picture is not obtained for free. In order that you will have a separatrix winding from the separatrix loop, you will need the characteristic number lambda of L to be smaller than 1. The characteristic number of M is mu, and in order to have the exterior separatrix to wind over the whole polycycle, you will need lambda mu squared to be greater than 1. But it is easy to achieve, and let us call this briefly by nu. Now we want to have a one-dimensional family with two arithmetic progressions, with two sequences of sparkling saddle connections first. And this one-dimensional family will be the following. When you unfold this vector field, you need to change three parameters. One responsible for the breaking of these saddle connections, another for the breaking of this one, and the third for the breaking of this one. So let us consider a subfamily where the first two parameters remain 0. That is, the two saddle connections of the heart remain unbroken. And only the loop is broken. Then this is a one-parameter family, subfamily of the unfolding of this vector field, of the perturbation of this vector field, one-parameter family E with a parameter epsilon. So we will have, at least in this one-parameter family, you will have at least two subfamilies of sparkling saddle connections. First subfamily occurs corresponding to these saddle connections. Second subfamily occurs corresponding to these saddle connections. For sure, both separatrices may take much more winds before the connection occurs. But in any case, on the line of the parameter epsilon, now, first of all, I plot the original parameter epsilon. You have a yellow sequence of, say, I, N, I for interior saddle connection, and another sequence of, say, E, M for the exterior saddle connections. And as I have written before, the double logarithm of IN equals to negative n log lambda plus O small, O large of 1. And it may be proved in the very same way that the double logarithm of IM is lambda is smaller than 1, and therefore we take minus to have a positive sequence. Nu is greater than 1, and so we take just logarithm nu plus O small of 1. Now suppose that there are two families, so you have the homeomorphic pictures, homeomorphic face portraits, but now everything in the second family is with tilde. We have a second sequence minus n logarithm lambda tilde plus O1 minus m logarithm nu tilde plus O of 1. And suppose that the two families, one shown on the blackboard, another similar to it, are equivalent in this sense. Then there exists a homeomorphism of the bases such that the corresponding vector fields have homeomorphic face portraits. First of all, consider a parameter value in the family E. And there is a family E tilde with the homeomorphic face portrait. These two families are the only subfamilies where the heart remains unbroken. So a vector field with a broken heart cannot be topologically equivalent to that with an unbroken heart. So the homeomorphism H from this definition brings, if exists, brings the family E to the family E tilde. Well, in the family E tilde, there is a parameter line and yellow sequence and pink sequence, again corresponding to the similar separatrix connections. And once again, a vector field with a separatrix connection between L, and we denote this saddle by I as interior, and this saddle by E as exterior. So if one vector field has a saddle connection between the saddle L and the saddle I, then the vector field in the other family should have the saddle connection between the similar saddles L tilde and I tilde, and therefore yellow points on one axis should come to yellow points on another axis. And the same for the connections between E and L. If a vector field has a connection between E and L, then the vector field with a homeomorphic face portrait should have a similar connection. So pink points will come to the pink points. And therefore, the two almost arithmetic progressions, I do not write the free terms here, are the two pairs of almost arithmetic progressions are topologically equivalent. So if exists H that brings the parameter values of homeomorphic phase portraits one to others, then this H restricted to the parameter line of the family E brings two almost arithmetic progressions, two other couple of almost arithmetic progressions, and this relation implies that if such H exists, then the ratio of these coefficients is the same for the two families. I put here structural stability in the title, but I forgot to say about structural stability. But I think you guess what I mean. A family is structurally stable if it is equivalent to any nearby family in a suitable functional space. So families like this are not structurally stable because for any family you can take a nearby family with the characteristic numbers of the saddles slightly changed, and therefore this equality will be violated. So exist structurally unstable families. So this is the end of the main body of my lecture, but I want to discuss another picture. I do not know whether the picture that I will plot is simpler than the previous one. And I have no proof that the corresponding family is structurally unstable. In my opinion, it is a challenging problem and probably a good problem for graduate students or even undergraduate, and it is the following. Instead of tiers of heart, consider just an 8 figure, one saddle with two separatrix loops. And let us try to simplify the situation. Suppose that the exterior saddle exists and its separatrices wind to this surface, and suppose that the interior saddle exists. I will write it now in blue. And its separatrices wind from. It is a temptation to find such a picture even for in a two-parameter families. One parameter is responsible for this loop, another parameter responsible for this loop, and all other is generic. But you will fail if this separatrix loop is repelling, the orbits are winding from it, then lambda is smaller than 1. It is easy to prove. If this 8 figure is attracting, then lambda is greater than 1. So this is a contradiction. The only neutral case is lambda equals to 1. And therefore, we are again in case of 3 degeneracies. 1 loop, second loop, and lambda equal to 1. In this case, this phase portrait is possible. It is not well written on the paper, but easily follows from what is written. But to investigate bifurcations in this family, to investigate sparkling saddle connections that definitely will occur when you break one separatrix so you have once again 2 sequences of sparkling saddle connections. For me, it is a hot interest to analyze this picture. Nobody have done it, and it is a good problem for the beginners in this domain. So I will stop here. My last lecture tomorrow will be called All About Singular Points of Analytic Vector Fields in the Plane. So this is the plan for people. Are there any questions?
So can we have families that are self-conjugated by some non-injective map of the parameter space?
Conjugacy by non-injective maps of the parameter space is forbidden, and I think that if you will allow them, you will not have reasonable extra freedom.
I mean that like there's a parameter space that is conjugated to a subset of the same parameter space.
I never investigated that.
No, I have a question. We have this separatrix loop, and there's a saddle inside, and we are drawing just part of the picture, and I'm trying to complete the picture in my mind, but I'm failing. So the saddle inside, the separatrix loop, how would we complete the picture?
So this is a separatrix loop, and you may have just an attracting fixed point, and everything winds towards it. This is not you are asking about, but the answer lies in this picture. You may replace this flow box by a so-called cherry cell. The cherry cell is the following. On the boundary of the flow box, you have the very same as before. but inside you put a saddle with this stable separatrix, this stable separatrix, these two unstable separatrices. Here is the source. And outside the flow box, you do not notice that you have changed something. And here, the saddle occurs. I do not reproduce the whole cherry cell. And you have its separatrix winding from the separatrix loop. Is it okay?
Yeah, but wouldn't that give problems with the continuity of the vector field?
No, not at all. It may be infinitely smooth. You use cut functions which are zero outside one neighborhood of one open set in this rectangle, one in the other open set of this rectangle, and you glue together vector fields in different pieces. Other questions? No geometric interpretation of beta because the interpretation is analytic. It is a coefficient. You have a map C to X over lambda. You can see lambda geometrically. If lambda is smaller than 1, then the map is like this, and if it is greater than 1, then the map is like this. So you can interpret lambda geometrically. But you cannot see this coefficient geometrically because it changes this graph to this graph. Different values of C. And giving the robust plot of the graph, you cannot distinguish different values of C. And beta is depending on this C. So beta has analytic interpretation rather than geometric one.
More questions?
Thank you.